Hello, I'm Scott Cowan and I'm joined today by Heather Amirault. Today we're going to talk to you about natural channel design methods in stream restoration projects. Today what we're going to go through is we're first going to touch on some design approaches, giving a brief overview of some typical and commonly used design approaches in Ontario. We're then going to dive into a case study for a project based out of Kitchener, Ontario, which is our Idlewood project. And then we'll kind of close it off with a discussion on takeaways and questions. Before we get started, I think it's an appropriate story is the 6 blind men and an elephant. And the story goes that 6 blind men come across an elephant in the jungle and they can only touch the part of the elephant that's immediately in front of them. As a result, some of them think that it's only a wall because they're touching the side of the elephant. Another man thinks that the elephants are like trees because they can only feel the leg that's in front of them. Another man thinks that elephants are like snakes because they can merely only grab the trunk of the elephant, and so on and so forth. Needless to say, they all have a different perspective on what they believe an elephant to be, purely based on only what's immediately in front of them. This parallels well with stream restoration design, where some methods, each method has pros and cons, and some do a better job of addressing certain components of a stream restoration design versus another. However, it's still important that you take a step back and see how it all fits together to kind of assemble a final stream restoration design, similar to only the legs, the trunk, the body, and the tail all kind of build together to build one entire elephant. We will now discuss different design approaches to stream restoration design. And before we do, we're going to have a brief discussion on typical variables in channel morphology. Some general two classifications exist for variables in channel morphology. They can be broadly classified into independent variables and dependent variables. Independent variables are things such as hydrology, like how much water is moving through your system, geographic setting, how steep is it? Is it in a really confined valley? Does it have good floodplain access? Sediment supply, is there a lot of material moving through your system on a regular basis? These are variables that you generally, more often than not, do not have any control over when you're doing stream realignment or stream restoration. And these variables directly impact the dependent variables. Dependent variables include things like channel width, channel depth, channel slope, and plan form. These dependent variables are what you would typically work with in a stream realignment design. Before we get into talking about specific design approaches, it's important that we note that we're only presenting 3, and this isn't a comprehensive list or discussion on all methods that are available to a stream restoration practitioner. It's merely a discussion on 3 commonly used approaches, and these are approaches that are typically used to define your channel morphology. They don't generally include a discussion on what your landscaping plan may look like in your riparian corridor, or what specific habitat features may look like from an aquatic ecology perspective. So the first approach that we're going to talk about is the analog design approach. This method uses reference conditions from systems that are either immediately upstream or downstream or adjacent to your site. And it uses the reference conditions to imply a morphology in your study area. And it takes dependent variables from those reference conditions to apply them to your site. The pros of this approach is that it's very easy to implement. It can also be applied at a variety of scales. So you can apply the reference reach approach on a reach scale for full-blown channel realignment parameters from top to bottom, or you can use it for individual components. And when I'm saying you can use these, it's important also to note that you can use some or more of the dependent variables that it produces. You don't necessarily have to use all of them. One of the cons is that there's an assumed constancy of independent variables. That is to say that your hydrology, geography, and sediment input in your reference reach should ideally be similar and or the same as your conditions in your design reach. Another con is that finding an appropriate reference reach can be very difficult. You don't always have ideal conditions, especially when you're looking in areas where you're trying to do restoration, where you may have a heavily impacted system. There may not be nothing immediately adjacent or nearby that can be used as an appropriate reach. Second approach that we're going to discuss today is the empirical approach. What this approach does is it's a relation of a dependent variable to an independent variable. So for instance, if you had a known drainage area, you could relate that to a specific width. This relies on a bunch of data points from a bunch of different reference sites collected into one data set to produce something like a regional curve. The pros of this is that it's relatively easy to produce a dependent variable or a dependent variable based on an input dependent variable. There's a larger data set relative to the analog approach. So using the reference curve, you could see where your data fits for your drainage area based on a variety of other reference sites with similar independent variables. The cons with this is that you're generally limited by your data set. So if you've got a reference, a reference reach, or sorry, a reference curve that's based in one physiographic setting and you're working in another one, because you're working in a different physiographic setting, the reference conditions may not apply. The third approach is the analytical approach. And what this uses is computation to derive any or all of your dependent variables. A good example of this would be hydraulic modeling in an instance where you need to define your water surface elevation during certain flood flows. The pros of this type of approach is that it's useful when your reference conditions are not necessarily valid. For instance, if you're working in an environment where you cannot find a good reference condition anywhere nearby, the analytical approach may be your most appropriate way to go. And your analytical approach could include a combination of a variety of different things, including sediment continuity and hydraulic modeling, hydrologic modeling, so on and so forth. It's also a useful tool in quantifying design components like water surface elevations and shear stress. The cons of this approach is that it can be limited by available data. So in other words, we've probably all heard the phrase garbage in, garbage out. If you don't have good data, you're going to end up with poor results. And it also means that you may end up relying on assumptions that may be difficult to calibrate in the field. For instance, if you don't have a good stream flow record on your site, it may be difficult to develop an appropriate design flow without that type of real field data. And you may end up relying on that data pretty significantly. In terms of determining your final design, again, we talked about 3 different approaches. These aren't the only 3 approaches, but in terms of your final design, it is best if you use a variety of different methods to kind of corroborate results and come up with some final geometry. In the Venn diagram provided here, you can see an example of how you could use the analog, analytical, and empirical approaches to come up with final geometry. Depending on your site constraints, you may find that you have to rely on some methods more so than others. So the example that I've been kind of coming back to is the analytical approach. You may need to use that more if you are in an area that has inappropriate reference conditions. And with that, I'm going to spin it back to Heather, and she can talk to you about how we've done design methods for a project in Kitchener, Ontario.
So I'm going to walk you through our Idlewood Creek project, which is just freshly built in the fall of 2018. So the images that you see here are either pre-construction or during construction. Here's a little bit of site context for you. The large water body that you see at the bottom right-hand corner is the Grand River through the city of Kitchener. The smaller water body that is joining the Grand River is Idlewood Creek. Now we're doing several pieces of work on Idlewood Creek right now, but I'm going to focus on the most downstream site, which is the portion of the site where the creek descends the Grand River Valley wall. To get a little closer to the site, here is where the creek intersects with the Grand River. You can observe that there is, or was historically, a large water body held back by a dam. So this led to an online pond, a dam, a pretty significant vertical drop, and the outlet was a gabion and basket channel. This whole configuration led to a pretty significant fish barrier from the Grand River upwards into the upper reaches of Idlewood Creek. One of the most important things to note here is the elevation drop across the whole site. As we're descending the Grand River Valley wall, we have a very, very steep system. The approach that we took to develop our design for Idlewood Creek included a mix of several of the design methods that Scott was talking about. For example, our analog type of approach did include a reference reach. We did find a reference style channel that descended the Grand River Valley wall, and we did evaluate that channel to define some of our dependent variables. We also used the channel form immediately upstream of where we were working to determine what a bankful channel configuration might look like. In terms of an empirical approach, we evaluated some of our dependent variables using regional curves. We also used a series of empirical bed mobility relationships to size some stone for this water course, since we know that the upstream area is very urbanized and our bed load can be expected to be pretty insignificant. And lastly, we followed up with putting our design into a hydraulic model in order to evaluate flood elevations, velocities, and specifically in this case, some shear stress. Here's one variable that we followed up on using all three methods. Bankful discharge, we verified it using the reference condition to evaluate how much flow was moving through the channel at bankful. We evaluated it analytically using return periods and some hydrology. And empirically, we compared it to a regional curve for the area. Overall, we used these three approaches to converge on a design bankful discharge. So in general, using our various approaches, you can see that we have the red line representing the former dam location, our orange shape representing the former head pond, and our dashed orange gabion outlet. All of that is going to be replaced by a natural system that is going to meander through a constructed valley and enter into the Grand River downstream of its previous confluence. We were able to reduce the slope somewhat in the system by extending the length of the channel, but as you can see, there's still a pretty intense valley curve happening here. Because of this curved valley, we went beyond our normal approach of a one-dimensional hydraulic model as part of our analytical review and put the design surface into a two-dimensional hydraulic model. Here you can see some output from the model as the valley curves. We were concerned that the water would want to go straight and kind of follow its old path, and that would put a high kind of shear stress and pressure along the newly constructed valley wall. So while that didn't happen exactly as we imagined, here you can see that the higher shear stresses are centered along the channel, but they're not as centered as we might wish, and they do kind of expand into the floodplain at a level of above 200 newtons per square meter, where we're not really expecting the vegetation to be able to withstand that on a regular basis. So what we would like to see is the orange and the red level of shear stress just more confined within the channel. In order to see some better outcomes and reduce the risk on our channel, we took a second look. Using the modeling and using our previously defined reference conditions, we were able to adjust some of our design parameters. We still applied some of the reference conditions. However, because your reference parameters result in a range of design parameters, our initial design was leaning towards one end of the range, and with our iterations, we were able to explore the whole range. For example, making pools more closely spaced together and trying pools more widely spaced. We were able to adjust the sinuosity. Our original design was quite sinuous, and the ultimate design has a reduced sinuosity. The most significant thing we changed was actually the floodplain grading, which doesn't come across through very many of the analog or empirical relationships. But we were able to see clearly through our two-dimensional modeling, as you see here, that the velocities on the floodplain are not well distributed. And so by adjusting the floodplain and allowing the water more equal access to the floodplain, we were able to make some changes. Here's a short graph that shows you how the changes that we made had an effect on the design. The pale blue line illustrates the shear stresses that you would have seen on the original design along the left outer bank full bench. So these shear stresses are in the range of 200 and 300, representing higher shear stresses than we'd like to see along the floodplain. Following the modifications that we made, the shear stresses along that outer bank are significantly reduced, which also reduces shear stress on the floodplain and puts us more at ease that our floodplain is able to hold up to flood flows without risk of erosion. Here again, we have the shear stress diagram showing a significant difference in the output based on our revisions. The original design has a wider range of coverage for the red and orange areas, which are shear stresses that we prefer not to have on our floodplain. Whereas the revised design, which you can see is a bit straighter with less sinuosity, it keeps the higher shear stresses more within the channel, where we have some control over keeping them from eroding the channel bed, and it distributes the lower shear stresses more widely across the floodplain.
The takeaways from this presentation are that stream rehab is quite complicated, which is no surprise to anybody, but there's no master manual associated with it. Every site is different and is going to require a different approach. To the second bullet, site conditions may dictate which design approaches are most appropriate. This is an important one. Not every site is going to be able to work with the same approaches, so you're going to have to modify accordingly. And every method has limitations. So, you know, we kind of outlined some pretty high-level pros and cons of the approaches that we presented. And it's really important that any practitioner, as they go forward on a stream restoration design, is well aware of the pros and cons associated with all of the approaches that they may be considering. It's sort of like going back to the story of the 6 blind men and the elephant. I mean, if you're only looking at the leg, you're not seeing the entire stream restoration design. Similarly, if you're only concentrating on what's going on in your low flow channel, you may be ignoring what's happening in your floodplain, which is what Heather kind of spoke to. And lastly, 2D modeling is an excellent way to add value and perspective to high-risk projects. This Idlewood project represented a site that had an elevated slope as a result of coming over the valley wall. Therefore, it was a bit more difficult to find an appropriate reference condition. And that's where the 2D model kind of became very useful, and it allowed us to evaluate what was going on in the floodplain, which would have otherwise not been doable in a 1D model. So that summarizes our presentation. Thanks very much for taking the time to listen, and we look forward to talking with you in the future.